All right, so here's our function. So the key observation to make at the beginning is to realize that x and y appear only in this key form, and so the graph is going to be rotationally symmetric around the z-axis. Right? So, by the way, I guess I skipped a step. I should first observe that the graph is z equals e to the x squared plus y squared. Graph means that. Right, so being as it is rotationally symmetric, that means that I can understand the surface. The axis of symmetry is, let's see here, the
z-axis. How do you know if it's symmetric around the z-axis?
Yeah, so it's symmetric around the z-axis. I picked a bad color choice there. It's symmetric around the z-axis because of the fact that x and y, and I should point down here, honestly, in this equation, x and y appear only as part of the special form, which is square root of x squared plus y squared. And this is that special form squared. Right? So x and y appear only in that form. So there's no stray x's and there's no stray y's other than as part of that expression. Does that make sense to everybody? Okay. Right. So because of that, it's symmetric around that axis. And that means that I can understand this surface, whatever it looks like, simply by understanding what it looks in any half plane hinged on that axis. Now, I have a favorite half plane hinged on this axis. My favorite such half plane is this one. And the reason why I like the YZ plane instead of the XZ plane is that the way we draw these things, the YZ plane looks like a rectangle. Right? And the XZ plane has a perspective issue that has to be dealt with. So it's just,
Would it be correct to use the XZ plane?
Yeah, you can use the XZ if you want. That's just a little bit more artistically challenging, and no big deal. Personal preference is fine. Okay, everybody on board? Okay. So, what can we say about that plane? Well, in that plane, x is equal to 0, and half plane, y is non-negative. And this, if I were to put it into there, the equation becomes, in that half plane, z equals e to the x squared. I'm sorry, e to the y squared. Sorry. Okay. All right. So now my challenge is simply to understand what this curve looks like in that half plane. Right? And here's where you have to, kind of do some single variable calculus kind of work. Let's think about, for example, let's start plugging in different values of y and see what values of z we get. You plug in y equals 0 and you get 1. If you plug in larger values of y, you get larger values of y squared and then larger values of e to the y squared. So it's kind of like that. Right? And as y approaches infinity, this function approaches infinity. Okay. So our surface is what you get when you take that curve and rotate around the z-axis. And so it looks kind of like a paraboloid, but it's not actually a paraboloid because it's got this exponential component to it. In other words, this is not a parabola, right? And so the surface is not a paraboloid, but it's got a lot of the qualitatively very similar features. So now learning what I've learned here, oh yeah, go ahead.
Sorry,
yeah.
Will it just kind of be like a skinnier paraboloid then?
It's a different shaped paraboloid. Yeah, it's skinnier the higher you go up, but it's got a different shaped bottom to it. So yeah, it's a weirder, different shape. Yeah. Yep.
So how do you actually, if you were to actually draw this?
Yeah, what I would draw is I would give two pictures. I would say that this is that curve, and then I would come down a little lower and say right. And then try to draw the surface itself, which is that. Right now, is this artistically? Is this frameable? No. Right? But you can see on the page what the curve is. I can see exactly what the equation of that curve is. And there's an indication that that curve is being rotated around the z-axis, and this then is, there's enough on the page to get an idea of where this surface came from and to get a rough idea of what this surface looks like. Does that make sense? You asked me this question? No. You did?
Yeah.
Is that all cool?
Yeah.
Yeah. Okay. Yes, you have a question.
Really quickly, why does it not matter that the x squared y plus y squared isn't in a radical?
Yeah. Okay, so this rotational symmetry argument says that x and y appear only as part of square root of x squared plus y squared. And so I think, if I understood correctly, your question is, there is no square root here, why is that okay? Is that right? Okay. So here's a way of addressing that. So let's look at the function again. The function is, the equation for the graph is e to the x squared plus y squared. And I could rewrite this as z equals e to the power of square root of x squared plus y squared squared. And so just rewriting a little bit, you'll notice that x and y appear only as part of that form. Is that cool? Yeah.
So it doesn't matter how you rewrite it, as long as for these, when would it matter how you rewrite that?
You're allowed to rewrite equations. I mean, equations that are logically equivalent, right? They're the same equation, and so you're free to rewrite to your heart's content, as long as you don't, actually change the thing. Yeah, right. Yeah.
So if you have this is number 3, z equals e to negative x squared negative y squared, it just be flipped across the y-axis?
No, it's different because that negative is inside the exponential, so that would change things a little bit. You want to talk about 4?
Yeah.
Okay.
How did that change things?
Let me get to 4 after we finish this one, but then we'll get to that. Yeah, we can do that right next. Yeah. Is everybody good with this one?
Yep.
Okay. Let me stop the recording.